Hello, and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Joined here today by Noah Gedrimas. He is the Vice President of Strategy at a fascinating company called GPR. And he's here to talk to us today about what they do and the technology and what he's seeing developing in his industry. So thank you for joining us today, Noah. It's great to have you on the show.
Thanks, Ryan. I'm really excited about being on this podcast and explaining a bit about what we do at GPR. And yeah, so looking forward to it.
Brilliant. If we could start, as always become traditional on the show, before we get into the company, tell us a bit about yourself. You know, we have a really wide listenership of the program, from younger people thinking about careers in science, technology and engineering, to older, more experienced people, VPs, C-suites in OEMs and tier ones. So it always amazes me the breadth of the show, but people are really interested in knowing what your personal story is. How did you get into doing what you're doing now in a really cutting edge business and environment? So what's your story?
I'm glad you asked. I'm one of those really fortunate individuals that knew from like a really young age what I wanted to do and, what I like. So, I was probably 5 or 6 years old, taking stuff apart at home and all through high schools, building cars and four-wheelers and working with my hands. And so I knew I wanted to be an engineer from really early on. Specifically, the mechanical engineering really appealed to me. So, race cars and vehicle dynamics and engines, transmissions, these sort of things. So that led to my undergrad, where I went to school in New Jersey for mechanical engineering and did a lot of hands-on projects, which is great about engineering, is you really get to, especially at the good engineering schools, work with your hands a lot. I worked on a lot of off-road vehicles, and then did some clean energy projects, which was probably my first entrance into robotics and mechatronics. So built a machine I was really proud of with a team called EHawk, which was electricity from high altitude wind with kite. So it's a great acronym our professor came up with. And we used this kiteboarding kite, and it could fly, hundreds of feet in the air and generate electricity from its motion. And so that had IMUs and cameras and different servo motors and things to control it. And that was kind of my first introduction to mechatronics and robotics.
Oh, wow. I've seen that on YouTube.
Yeah, exactly. Yeah. So we were really early. That was back in 2013 or so. We were working on that. And, up to that point, all my engineering had been a lot of, using pulleys and gears and 4-bar mechanisms to get things to happen in a certain way, in a certain order, sort of traditional mechanical engineering. And then once you are exposed to, we used a lot of Arduino stuff then, microcontrollers and servos and sensors, you realize how powerful they are and how quick you can change things and tune PID controllers, things like this. And it just grabbed my attention immediately. And I really dived into it there. And later that summer, after that first EHawk project, I got an internship at Virginia Tech at the Transportation Research Center, I think it was called, or something to that effect. The project was to build a chassis of a 1/5 scale of a Audi vehicle that the grad students could program to autonomously park. So first I built the chassis with the crux steering and servo motor and whatnot to steer it, and then had time left over the summer and then programmed it and made my own algorithm to do self-parking using an ultrasonic sensor. And that was massive for me. That was sort of the introduction to autonomous driving there. After that, I started learning more and more about it. Right then was when Chris Urmson was talking a lot about the Google autonomous driving project at the time. It was before Waymo. And I was learning more and more about that, and really grabbed my attention. So then graduated undergrad, moved out to Michigan to work in the auto industry. So I always say, most mechanical engineers end up passing through Michigan at some point. just because of the huge auto industry there, and there's so much. So I did like some mechanical stuff, like belt drives and things like this, CVT design at Gates Corporation for like 3 years. Went to get my master's degree then. And I still remember I was in a vehicle dynamics class in grad school. And my professor was worked at Continental Automotive as a tire engineer. And at the time, all I knew about Continental was they made tires, really. But he took us to visit the engineering facility in Auburn Hills, Michigan. We sort of saw all these things. And one thing I saw there was an autonomous vehicle Continental was building called HAD. It was highly autonomous driving vehicle. It was like a level 4 highway autonomy vehicle. And I still remember like the class trying to go back to the university, to Oakland University. And I was there for another like 30 minutes and they had to drag me out of there because I had so many questions I was learning. And I just got back later that night and I was thinking, I just had no idea that there was this autonomous driving development happening so close to me. I just always thought, oh, that's all the stuff they're doing in California and, in Pittsburgh. And, these are super elite people working on this. And then to see it so close, I just completely shifted my career. I moved my degree into more mechatronics focus and more controls and I still have the emails, like 12 separate emails over a year to the Continental team that was working on, just saying, hey, here's this MATLAB script I wrote, or here's this paper about autonomous driving I thought was interesting. Would you please hire me to work on this project because I want to do it. And finally, like everything aligned, they hired me.
They gave in.
Yeah, they gave in. And I'm still really good friends with the hiring manager that hired me and kind of took that chance because I was getting good at like belt drive design, the serpentine belts at Gates. And that kind of scared me. I was like, I don't really want to be an expert in rubber belts. I want to learn something else. So then I went to Continental and had just an incredible experience there. I spent 7 years doing research and development for different autonomous driving technologies. So everything from that highway autonomy project to electric shuttles, like passenger shuttles that you'd operate on a college campus. Did some projects with Easy Mile, did valet parking, and we called holistic urban driving. So autonomously parking cars in parking garages, semi-truck autonomy. So you might have heard about the Continental Aurora partnership. So I was a little bit engaged in that towards the end of my tenure at Continental. And it just was this incredible experience for me because I got to learn about all the operational domains, all these different technologies that go into autonomy and then apply them in the real world. And about 18 months ago, I joined GPR. And so GPR is the company I'm currently at. It's a startup. We're out of Boston. We really have a different approach towards localization and mapping for autonomy. And I jumped over to GPR because my experience at Continental, I knew what a gap this was in so many operational domains that I was really excited to be a part of it. So that kind of takes me through most of my autonomy career. But
what was it that caught you and dragged you in?
I really like this the first principles thinking, that you can apply to different engineering challenges. And in the space of autonomy, there's really 3 or 4 big problems that you need to solve. And most of the biggest problems are perception based. You need to perceive dynamic objects, which are things like moving cars and pedestrians, and that's where prediction comes in. You need to detect sort of static objects, which is like free space detection, and that's seen as there a free area to drive. And lastly, you need to know what I call drivable area, and this is sort of where a vehicle can navigate, and there's enough road surface to support the vehicle, and it's a driving lane, so you're not driving on the sidewalk, let's say. Even if it's free space, meaning that it's there's no objects in the way. The first 2 you really need perception for. So for dynamic objects, you need to have good cameras, lidars, radars, whatever the case is, to see what's around you. Similarly for the free space detection, but for the drivable area portion, almost every company uses mapping and localization. And so basically, the mapping portion is you have this pre-existing understanding of an environment where the driving area is. That can be very helpful for a lot of operational domains. But then to really effectively use that pre-existing map, you have to have localization. And you have to know where your vehicle is with a high accuracy. when you're trying to solve the localization problem, really all localization methods use some sort of a landmark or some sort of a datum that you're measuring with your onboard sensors on your vehicles. And then you know the position of that datum relative to, say, the lane center or crosswalk, the feature you care about. So examples of this is like maybe lane markers, right? So you often will use a camera to detect the lane marker, and then you know the lane marker's position relative to the center of the driving lane. So that's one way you can align the map. Other more common ways are like GPS or GNSS based. And in this case, the landmark is a satellite, so it's really like a space mark, but in general, same principle. You're measuring your position to a satellite and then the position of the satellite to your map coordinate. Back to kind of the first principles aspect of it, if you're trying to choose datums or landmarks that you want to use for positioning, what's important in those landmarks? I always think you want them to be resilient over time. So you don't want them moving or changing. So for example, if you're trying to use trees or lane markers, you don't want the lane markers wearing off the road. You don't want leaves falling off the trees. If you're trying to use the edges of a parking garage, you don't want a car to block your sensor's view of the edge. That's really where the GPR comes in. So the ground penetrating radar that we use allows us to take data from actually underneath the surface of the road. So up to 3 meters deep. So we're still using landmarks or data to position, but our data is coming from underneath the car, meters beneath the car. So we're not like reinventing the concept of landmark localization. We're just using data from underground. Yeah. Yeah, mine was too. When I first was exposed to it, my first thought was, well, wait a minute, if that works, that would be great because my sensor's never blocked. So if you're trying to use a LiDAR to detect, let's say, signposts or telephone poles or even lane markers, if you have a semi truck in front of your vehicle, your LiDAR or your camera or your radar or whatever you're trying to use can no longer see the features you're trying to localize off because they're blocked. And that's not even bringing in, adverse weather, right? So if it's snowing or it's raining or this, those also block your sensors. But if you're looking down, we never have anything that gets between the ground penetrating radar and the data layer. So we have 100% availability.
What do you do with that? How do you make that work into something that's then a useful reference?
So that's really what grabbed my attention. So on a first principle standpoint, when I was looking at this before I joined, I said, this is a extremely powerful idea. If you really can pull subterranean data and use that as the data, and if you can see through a meter of concrete with your radar, a layer of snow or mud or debris or something like this isn't going to affect it very much at all.
What are you getting out of that subterranean data?
So that was my question, right? So I said, okay, that's a cool idea, but does it work? That sounds cool, but does it work? And I had a lot of interest in, well, is the data unique enough? So the data that's coming out of the ground from this section of highway to, move 20 centimeters forward, is there a big enough change in the subterranean environment to position with? What type of features or landmarks are you using underground? And how do I know that they're not going to change over time? So as sinkholes are forming and the ground shifting and moisture's going in, how do I know the return's not going to change? We're not using specific infrastructure. So that's important to note. So it's not like we're explicitly looking for pipes or rebar or different layers in concrete. We're looking at the radar image itself. So we're looking at the return from the radar, which is giving us sort of different intensity profiles for different depths and for different channels of our radar. And then we're using that sort of landscape, or you could think of it sort of like a point cloud. It's not really a point cloud. We can think of it sort of like a point cloud. And we're pulling out distinct features or character that we know will hold up over time and is highly unique. And then that is the matching element. So an example, it's not perfect, but you can kind of think of it like maybe a QR code. So when you're looking at a QR code or a fingerprint, it's not that there's some like big star in the middle that you're matching, but you're taking the profile of all the areas where white goes to black and black goes to white in a QR code, and then you can use that as a matching element. So in the same way, that's how our matching works.
are you creating like a map of that data and using it in a kind of absolute sense, or are you using it for sort of relative, so you can judge speed, for example? Because I know people do use radar for particularly off highway for trying to judge speed. Like, what are you actually using that for? How do you use that data?
So it's a landmark localization, which means it's like a map and track. So we have to map an area beforehand to understand what that subterranean data looks like. And then any other future vehicles that pass over that area can localize or position with, centimeter accuracy. So it's a map and track. And there's really two kind of implementations that get applied, where you can look at sort of the high level driving mission. The first is what we call the, virtual rail, or almost like a virtual train track. And with this concept, you have the mapping vehicle, or the first vehicle to drive, records the subterranean data, this GPR track, and the data is roughly the width of the vehicle. And we can record a route. So, for example, if you had a shuttle application that operated a college campus, you would have to drive the shuttle manually on the driving route and then record that as a track. And then all future vehicles, including that vehicle that want to autonomously follow that track, can log their current GPR data and match it to that map and drive entirely based on the GPR, almost as if you had put down, a line of paint on the ground, and then the vehicle follows that line of paint. So that's good for certain applications that are quite simple. So think like mining use cases, where you have the truck going from the excavation site to the dump site or the plant, where they're driving the same haul road route repeatedly.
Terminal tractors and things like that?
Exactly. Terminal tractors is another big use case. Port automation, convoying is one. So like platooning cases. What's really nice about how we make our maps is there's no post-processing. So you can do sort of similar technologies using a LiDAR or a camera. But in a lot of cases, if you were to take a LiDAR system, drive it on some college campus route, and then have an algorithm extract features for localization, what you'd find is that certain portions of the route, you'd have parked cars that are blocking the LiDAR's view that were there during mapping. And then when you go back to localize, those cars might not be there. So a lot of times you have to manually go and edit out the dynamic or semi-dynamic objects out of your feature map. With GPR, we don't have to do that. And so you can build a map, or anyone can build a map. So it could be just a construction worker, a mining operator can drive a truck once manually in a mine site, and then that route's ready to be used. So it's a very fast way to iterate. So that's virtual rail. The other way we can use GPR is more traditional, like a GPS type of an output. So with that, we can map a bigger region. So we could map, say, an entire highway section or a seaport or something like this. And then anywhere that a GPR equipped vehicle navigates over that map, we can output coordinates. So usually WGS84, like GPS coordinates that can be brought into the autonomy planner. So that's a more traditional type of a localization that some of our customers are more comfortable with.
You're saying you could drive on that alone. Do you see this as being something that you would use in environments where you didn't have good GPS, GNS, or is it sort of as well as, or like how does it kind of fit into the technology stack?
It can be integrated with GPS and other inputs, and some of our customers do that. In some of our applications, there's no GPS at all. So for example, underground mining, which has been sort of one of the most challenging operational domains for autonomy, has been underground mining. And it's because the environment changes so much. It's incredibly dusty and harsh, very hard to have any robustness in that environment. And localization is a massive challenge because ground truth is pretty much impossible underground. So in those applications, there's no GPS fusion at all. And it would be purely GPR based and odometry. So we do use like a wheel speed and a IMU to help sort of supplement the position of our GPR scans relative to each other. It's GPRs can be the only absolute reference. In most of our applications, that's the case.
So genuinely, I've learned something new already, and I hope, I guess some listeners would as well. Where do you see the market for that going? Is it something that you would see kind of all autonomous applications potentially bringing in as another part of that sort of sensor fusion, or is it going to be only kind of certain applications where they really take a benefit from it? Is it is it a mass market thing that we'll see everywhere, or something that'll be underground mining and terminal tractors and stuff like that?
Yeah, so there's really a broad range of applications for it. And so I'll talk about some of the ones that we're most engaged with now. So the long term is definitely automotive. So the highway automotive, so you could think like GM Super Cruise and Ford Blue Cruise, these type of applications. The real challenge with those is the packaging of the sensor. So the sensor, it's only about an inch thick. It's 80 centimeters wide though. And so packaging that underneath the car requires a lot of forethought from the beginning
Yeah.
to integrate, and then to get down to a cost point that's appropriate for automotive passenger cars as well. That application, I think it will come into play, but probably not until we see more level 3, level 4 vehicles where customers are that's a bigger selling point of the vehicle. The other industries, though, the ones that appeal to me the most are the markets that are already mature and already deployed. So, for example, the mining, the off-road mining, specifically in sort of Australia, South America, Komatsu and Caterpillar and some extent Hitachi have been doing this for decades. They've had trucks deployed, the business case is sound, making money, and they have big challenges in these regions now with localization. So there's a lot of solar, like ionic scintillation events that can cause issues with GPS and bring those fleets down. And so GPR can be applied there to an existing business model that holds up. And so we'll see it there pretty early. Similarly in seaports, so unloading containers off of ships and moving containers in seaports. This is a great application for it as well, because the robustness needs to be really high, and it's a really infrastructure-aided localization now. That's a big case. The electric shuttles, they always seem to be electric, but the passenger shuttles that are maybe a little bit slower speed, usually under, say, 40 miles an hour. These are good use cases as well because it's very easy for us to map and track in different locations and get a really high safety integrity level with that. So that's a big space for it. So really anywhere where autonomy is safety critical and it's fairly consistent, it makes a lot of sense to apply GPR.
Could you tell us a bit more about the technology itself? I mean, what is the sensing? You describe physically quite a broad sensor element. What's in there? What's making that work?
Yeah, so we have a series of antennas that work in a very low wavelength of radar. We're in the hundreds of megahertz, the ultra wideband, and this allows us to penetrate meters through the surface of the ground. Now, for emissions reasons, we have to keep the power levels really low, so that the whole sensor is only outputting 9 watts, so it's a very low power sensor. There's no moving parts, so it's very robust. I often described as a metal box with some wires in it. That's important for a lot of applications, especially when you're mounting on the underside of a vehicle, that it can hold up for 10 years and really be a robust part of an automobile. And yeah, I mean it's in some cases, in some ways, simpler than a traditional automotive radar, like a 77 gigahertz radar.
A big part of it must then also be the sort of analysis of and processing of that data. Is that, are you guys doing that, or do you just, how does that work?
Yeah, so there's kind of 3 phases to applying the GPR data to the final position. So first is the detection. So then, we have RF chips on board the sensor that are, transmitting and receiving radar returns, sort of profiling the ground, creating that image, that GPR image. Then there's some signal processing that runs on board the sensor, and that's really the special sauce that took so long for GPR to develop, and that's extracting the data that's unique and that holds up or doesn't change over time. If you just took a sort of off-the-shelf GPR unit and tried to do localization, you'd find that the data is changing quite rapidly for different regions, and the sensor would be quite large and be hard to use. So there's a lot of signal processing that happens on board the sensor. Then the that data is transmitted usually to a secondary ECU. So like our development kits, we have a PC we ship, but it could run on the edge of the customer's computer. In some cases, we can run it inside the sensor, and it runs the matching. And so that's taking the current GPR image and matching that to a pre-existing map. And so that's sort of like a pattern recognition matching algorithm. And then once the match is complete, it will output a position, usually with a centimeter level of accuracy, and forward that position to the customer at up to 50 hertz. So 50 times per second, we can offer 1 centimeter accurate positions. And then that can then be fused with the GPS solution or other solutions, or it can be used directly.
There's quite a lot of technology actually in the sensing element itself.
Yeah, we make the hardware. The hardware is custom and has lots of years of development in it. And then there's a lot of signal processing and then matching algorithms and localization and mapping algorithms. So we have a really incredible team at GPR that covers a wide range of engineering from RF to mechanical design to algorithms and even some machine learning. So
Can you tell us a bit more about the business itself? I mean, it sounds amazing what they're doing. How you mentioned you've been there for 18 months, but presumably the business has been going a whole lot longer. So, what's the origin story of the company?
yeah, sure. So the technology came from MIT's Lincoln Laboratory out of Cambridge. One of the inventors was our co-founder Byron Stanley. So he invented the technology while working, I believe, on a mine detection using ground penetrating radar for the military. And at some point, I think they noticed that the returns from the radar were quite consistent on routes, and came up with the idea of LGPR, or localizing ground penetrating radar, or maybe it's ground positioning radar, and started developing it at MIT. Wrote some great papers about it. And then Byron worked with our other co-founder, Tarek Bolat from Harvard, to found the company in 2017. It was found, the name then was WaveSense. And since 2017, we've spent about first 5 years really making the sensor much smaller, much cheaper, much more robust, and meet emission levels, while bringing the performance up so that it could meet the automotive market. And so that's really been the focus since then. Starting really at the beginning of this year, we had a product that we were ready to commercialize. And so sort of scaling it to higher volumes so we can build more of them, testing them in more challenging environments, and then really making it a generic product that can be applied to a lot of different applications. That's something that takes a really special type of engineering skill to be able to have a product that can be easily integrated into a dump truck, and then an electric shuttle, and then a robo-taxi. And I actually just talked to a company about putting on a legged robot. So there's all kinds of really cool stuff that we need to be applied to. So that's a bit about the company. We're still out of Boston now. We're in the Somerville area. We're around 30 employees.
Have you got these things on application now? So presumably you've been doing quite a lot of testing in-house and kind of making as you've been developing it, but a bit more about that.
I think I could talk a little bit about the spaces the customers operate in without using their names at this stage. A lot of the operational domains we're working in, we're learning with the customer about how does the GPR fall into the functional safety plan. How is best to integrate it? Should it be an independent localization modality that gets used as a redundancy to the other localization, or should it be fused? Should they do the fusion, or should we do the fusion? These type of things. And it varies a little bit from customer to customer. So some of the more mature engagements, we have a great engagement with a defense contractor that's using it for sort of military vehicle, convoying and moving of autonomous vehicles on the battlefield. We have 2 electric shuttle companies that have systems that are working on move electric shuttles of different sizes and different price points. We had a last mile delivery project, delivering food. There's a couple of mining cases So one of them's the rigid frame haul trucks that you see, those huge trucks in South America. Then there's sort of a middle mining project, which is moving, ore kind of from a mine site to a coast using more traditional semi trucks like level 4 trucking. And then one of our biggest engagements now is for seaports. So guiding AGVs, which are the vehicles that move the containers from the cranes that unload the ships to the stacks in the different seaports around the world. And underground mining is another case that's quickly ramping up as they're sort of discovering the possibilities there.
And what stage is it at? Is it kind of our customers actually using it in working systems, or are you prototyping with them, or is it sort of pre-trials, or like is there a fleet running on these things already, or where's that at?
Yeah, so none of them are in commercial use currently. They're all being used for development of future product. And there's a couple reasons for that. So the first is that some of the products that our customers are working on, they haven't released yet, right? So they're electric shuttle programs that they have, big ambitions for high volumes, but they won't hit for another year or so. And we're the preferred GNSS denied solution for theirs. So we still see them as sort of one project. The other case is that we've been delivering these commercial products just this year. So before this year, it was much more research based, sort of gaining understanding. But we just released our B sample sensor, which is the first one we'll enter any kind of volume production with. Yeah, so within a year here, next year we'll have fleets operating, and we have a fleet of 5 vehicles as well that we use for development.
That's really fantastic. And in terms of where autonomous systems are at the moment, obviously it's a very hot topic with that ability to accurately position vehicles and detect objects, and there's lots of different views on the best way of doing that, and achieving sensor fusion, and lots of radar systems and all sorts of things. But this is genuinely sounds like something new that isn't particularly out there, and I guess it's not every day you come across that. So it's fascinating to learn more about that and where you're at. I guess it'd be interesting to know more about like where you see this going, and what your kind of thoughts are in terms of the technology development. Like, what's your critical milestones in the next 12, 24 months?
Where we're really going with this, there's one really big advantage to what we're doing over other types of map and localization, and it's that our data layer is really small. So the data coming from the radar, it's very unique, and our field of view compared to other sensors is quite short. So we're seeing 3 meters deep, but 3 meters, with the field of view, the width of the vehicle actually amounts to a pretty small amount of data. You compare that to like a LiDAR or a camera that's looking hundreds of meters. And so what that means is that our data layer for huge swaths, like entire cities, is very small. And that allows us to do a crowdsource map build and crowdsource map updating with over-the-air updates. So we could quickly get to a point where we can be building maps of entire cities or road networks using the data from customer vehicles. So you could have a case where you install GPR units on a few thousand vehicles, and then those vehicles just in normal operation can expand the map to in the entire highway system of the U.S., let's say. So that's one of the the bigger ambitions is kind of building that out and becoming sort of the anchor or the ground truth for all other maps to operate on. And that's something that I feel particularly passionate about, because I think that this idea of we're constantly updating maps because the surface environment is changing really is a huge limitation for HD mapping for autonomous driving. And it's very expensive to update maps as well. For example, if you had a map of a section of city and it's 2 years old, and then you want to go and update that section of maps, you drive a mapping vehicle through that has cameras and radars and lidars to detect lane markers and different features, it can be very difficult to align the old map data to the new map data. And you would think that, well, GPS can work, a high accuracy GPS. Well, actually, because of the motion of tectonic plates and things like this, the GPS ground truth drifts kind of over time. And it's difficult to lock things together, especially if you're talking about long sections of data. If you mapped 100 miles in one direction, it'd be difficult to match that up. So you're looking for other references or datums. And since GPR, we're using this subterranean data that's not changing over those timeframes, we can use that as an anchor to lock together different maps and become a sort of geo reference for all other HD map layers. So that's one thing that really excites me. It's a little bit farther out on our roadmap. In the shorter term, we're really focused on the customers that have business models that are proven right now, right? So examples of this are like the mining case, the seaports, this electric shuttles in some cases. Those are really appealing where, we've been sort of hearing the promise of some of the more ambitious autonomy projects for years, and they're, sort of delayed. And we're enabling technologies there. So we're still engaging there, but we know we can bring value to some of these customers today that already have marketable business strategies in autonomy. And so that's really where we'll be in, a year's time, is enabling certain companies to expand their autonomous offerings to more operational domains. So for example, you had an above ground mining autonomy system. Now you can sell that mining system to below ground, or you can increase the availability. Similarly, maybe you had the airport logistics vehicles that move the baggage. Before, maybe you couldn't sell those in airports in the Northeast of the United States because of the snow and the winter conditions, and we can help enable those companies. So that's really where I think GPR will be applied first, is where it's really easy to make that business case that if you can enable localization in adverse weather or in this environment, then we can make more money. And so that's probably the short-term goal.
Looping back almost on myself, it just kind of occurred to me thinking about what you said. You mentioned about like a biped robot, but something just occurred to me as I recall talking to someone a few months ago. It was about the application of robotics inside buildings, sort of more generally, and for things, service robots for cleaning, and stuff like that. And the I specifically remember that one of the problems inside the building is that they kind of, the localization element is really difficult. Effectively, your cleaning robots end up very expensive because they need such comprehensive LiDAR suite and all the rest of it that it actually doesn't kind of work out. Would your technology work in buildings, in that kind of application, so for lower cost?
Yeah, absolutely. So some of our applications are indoors. So we have factory automation and warehouse automation fall into that category. Actually, one of the biggest proof points for me when I joined was parking garages. So we mapped out a multi-story parking garage and drove autonomously in it with a GPR system. And parking garages, the multi-level garages, they're often built out of these spancrete, they're called slabs, where they build these concrete slabs in a factory. Sometimes they're only, maybe 50 centimeter or not even 30 centimeters thick. So they're quite thin. And, we're seeing meters normally. And they're all made in a factory, and they're all, you would think, would be very homogeneous and not lend well to localization. But actually in these multi-level garages, we're able to localize just fine, even with that small amount of data from the concrete. And in some cases, it works even better than on the surface street. So that was really quite cool to see. And we tried it on like different levels and things to see. We could, some cases, see straight through a level and see cars below, which was kind of cool. But yeah, indoors it works well, and it's being evaluated for AMRs, which is automated mobile robots, and that's for actually in a car factory for moving things around. So yeah, it works indoor as well.
Like those robots in factories, quite often they end up putting like tapes or tracks down as a sort of cheap way of, so they are guided, they're very definitely guided, but those systems can be damaged and require maintenance.
And then if you want to change the route, that can be a challenge. So that's where they found the GPR appealing, is well, wait a minute, if I wanted to change the route or or have the, robots go over here instead of over there. Says, yeah, all you have to do is drive that path once manually by manually driving it, and you have a track that all the vehicles can follow. And that was quite appealing.
It's much cheaper than a LiDAR type system then?
Yes.
Yeah.
Yep.
Okay.
Yes. Particularly once we get to, volume, will be significantly cheaper. So for like automotive volume, we should be on par with like a premium automotive radar today.
I'm going to go away and lie down in a darkened room and absorb all of that. Thank you. One absolutely amazing business. And yeah, thanks so much for telling me about your technology. That definitely sounds like it's going to be one to watch for the future.
Yeah. Well, thank you so much for having me, Ryan. I really enjoyed it. And yeah, to any listeners that are interested in learning more about it, feel free to reach out. My email's noah@gpr.com. So pretty easy. And yeah, there's lots of cool applications and research projects and things we're looking forward to in the future with this. So
Fantastic. Super fascinating. Absolutely brilliant. And so you have managed to, you blow my mind, which is quite hard to do, but just something that I had not even heard of, let alone thought about. So amazing. Definitely going to keep a close eye on you guys in the future. Thanks, Noah.
yeah, thanks a lot, Ryan.